November 16, 2006. Routine shutdown on a Bellevue construction site. A veteran crane operator checks his bolts and logs a troubling deflection. 5 seconds later, 210 feet of steel collapses, shattering buildings, ending a young life, and forever changing Washington's crane safety laws. This is the real story behind the $5 million Bellevue crane collapse and the warning signs no one acted on. What really caused steel to fail so silently? Warren Yeakey started his shift in the cab of the Liebherr 112 ECH, 210 feet above the Bellevue streets, just as he had every day for months. At 34, with a decade of crane work behind him, he knew the smallest change in the machine's mood. Before powering down for the evening, he followed his ritual. 16 M24 bolts at the base, each torqued to 300 Newton meters, checked and rechecked by hand. He logged every reading in his notebook, noting a base deflection of 25 millimeters, more than double the manufacturer's limit. It was an uncomfortable number, but the site superintendent had brushed it off as normal settlement. Still, Yeakey's instincts told him something wasn't right. Inside the narrow cab, he listened for the familiar whir of the diesel engine idling, felt the subtle sway as the boom settled at its 45-degree angle. The city below was winding down, sunlight glinting off glass towers. Then, without warning, a sharp crack echoed from below. For 5 seconds, the floor beneath his boots began to shift. The sensation was unmistakable, metal giving way, the world tilting. Wind rushed through the open window as the mast pitched north, 30 degrees in an instant. Yeakey grabbed the controls, bracing as the cab lurched sideways and wedged against the building's edge. The violent motion threw him against the glass. He crawled through twisted steel, blood running from a cut on his forehead, heart pounding. The radio in his hand shook as he pressed the button. "It's down." Firefighters arrived within minutes. Lieutenant Bruce Croon led the rescue, extending ladders to the battered cab. Yeakey, dazed but conscious, climbed down on his own. He'd survived a 20-foot fall inside a mangled shell of steel and glass. Later, he would describe the moment. The instinct to grab the stick, the sense that something had gone terribly wrong, the knowledge that he had done everything by the book. For Yeakey, the memory of that 5-second warning, the crack, the sudden shift, the scramble to survive, never faded. He knew every bolt, every vibration, every sound in that machine. On that afternoon, the warning signs were logged and real, but the silent failure beneath his feet had already begun. At 4:15 in the afternoon, the heart of Bellevue was transformed by the collapse of a 210-foot Liebherr tower crane. The mast, once upright and steady, dropped 30 degrees to the north in seconds. Steel shrieked as the base sheared away, sending the 15-ton counterweight arcing nearly 100 feet through the air. The city's pulse stopped as a debris field spread across 200 feet, swallowing cars, sidewalks, and the lower floors of 3 buildings. Glass shattered in sheets, raining onto the street from the Civica office tower and neighboring apartments. Steel latticework, once part of the crane's core, punched through 15 inches of asphalt and embedded itself deep in the parking lot below. Concrete pillars snapped, the counter-jib whipped around and smashed through the parking garage, scattering fragments across the block. Inside a 12th floor apartment, Matthew Ammon sat surrounded by the ordinary comforts of home. The wall behind him gave way in an instant as a section of the crane's structure tore through the building's skin. Ammon, just 31, a Microsoft attorney with a promising future, was killed instantly. The violence of the impact left no time for warning or escape. His parents, Larry and Kathleen, would later speak of his love for music and his dedication to justice, traits that made his loss resonate far beyond family and friends. Across the street, glass facades bowed and buckled, sending shards into offices and onto the sidewalks below. Steel beams, some weighing thousands of pounds, landed with enough force to crater the pavement. The debris blanketed a 200-foot radius, leaving vehicles crushed and storefronts gutted. Residents and workers poured into the streets, stunned by the destruction. The city block, once bustling with the rhythm of daily life, was left scarred and silent. The collapse was not just a failure of steel and bolts. It was a disaster that reached into homes, offices, and the lives of everyone nearby. The scale of the destruction forced a reckoning with the risks embedded in the city's rapid growth. For Bellevue, the loss of Matthew Ammon became a symbol of the hidden stakes behind every crane that rose above its skyline. The aftermath demanded answers, not only about what failed, but how a single engineering decision could ripple through an entire community. By 2006, Bellevue's skyline had become a forest of cranes. From the city's core to its edges, more than 24 tower cranes worked above the streets, their booms swinging over new office towers and high-rise condos. Developers raced to keep up with the flood of technology companies expanding into the region. Microsoft's growth alone drove demand for millions of square feet of premium office space, with Class A vacancy rates dipping below 5%, sometimes as low as 3.8%. Every new project promised to fill before the last window was even installed. Permitting records told the story in numbers. Annual commercial building permits jumped from around 180 in 2003 to over 240 by 2006, a pace that outstripped even Seattle's downtown. Construction managers juggled not just blueprints and schedules, but the relentless math of delay penalties. Contracts for projects like Tower 333 included liquidated damages of $15,000 for every day the job ran late, with weekly penalties sometimes topping $200,000. For a $100 million office tower, a single week's delay could erase months of profit. With so much at stake, every piece of machinery became a critical link in a tight chain. A single hour of crane downtime didn't just slow the work on one floor. It rippled through the entire site, backing up deliveries, idling dozens of workers, and straining relationships with investors watching the clock. Maintenance contractors faced their own pressures, with bonus incentives tied to uptime, not caution. Inspection cycles stretched as crews tried to avoid triggering stoppages that would cost thousands before lunchtime. The city's appetite for new space meant that residential towers filled up almost as quickly as they opened, with occupancy rates of 80 to 90% within half a year. The absorption rate for office space, over 2 million square feet per year, set records for the region. Developers, architects, and contractors all felt the squeeze, the need to deliver fast, to innovate, and to keep the skyline growing. In that environment, even a minor design shortcut could seem like a smart bet, a way to save $500,000 or 2 weeks on the schedule. The boom years brought prosperity and optimism, but they also introduced risks that would only become clear when the pressure finally overwhelmed the system. The decision to build the crane on an H-frame grillage rather than a traditional concrete pad started as a solution to save both time and money. The site's parking garage, still curing below, made a massive concrete foundation impractical. Instead, 4 concrete pillars supported a welded frame of W14 by 30 steel I-beams, bolted together and anchored at each corner. This approach shaved $500,000 off the budget and promised to keep the project moving on schedule, 2 weeks faster than the usual method. But the shortcut came with hidden risks. The engineering drawings called for temporary steel ties to connect the crane's base to the building's concrete core. These ties would provide about 40% of the lateral resistance needed to keep the mast upright against wind, slewing, and the shifting of heavy loads. The plan assumed the core would be poured and the ties installed before the crane saw full service. But as delays stacked up, 8 weeks waiting for the garage slab to cure. Those ties never materialized. The contractor pressed ahead, working around the missing support without formally notifying the engineer. On paper, the system looked complete. In reality, the base stood alone. Without the ties, every wind gust and movement of the boom put extra force on the H-frame. Calculations after the collapse showed the base had to absorb up to 250% more lateral load than it was designed for. The steel I-beams, with their T-shaped cope cuts and web stiffeners, became focal points for stress. Each weld and bolt, meant to act as a backup, now carried loads that should have been distributed through the building's core. The 16 M24 bolts at the corners were designed for shear, but not for the relentless, off-axis twisting that built up as the crane cycled through daily work. The geometry of the H-frame, sharp corners, cutouts for stiffeners, and the absence of continuous bracing created natural points of weakness. Stress concentrations at the weld toes multiplied the force on small areas, increasing the risk of fatigue with every turn of the boom. Over months, vibrations from idle engines and slewing amplified the problem, loosening bolts and accelerating microscopic cracks. The design relied on a chain of assumptions: that the core would be ready, that temporary conditions would be short-lived, that each piece would do its part. When those assumptions failed, the entire base was left exposed. For the engineer, the calculations stopped at the boundary of what was communicated and confirmed. For the contractor, the pressure to keep the schedule left little room for pause. The result was a foundation that looked sound from a distance, but was quietly accumulating damage at its most vulnerable points. The decision to gamble on speed and savings set the stage for a failure that would not reveal itself until it was too late. Ironworkers on the Tower 333 site felt the tremors before anyone else. Each morning, as the crane idled and the boom swung to rest, a low-frequency vibration rattled through the H-frame base, 5 to 10 cycles per second, enough to make tools dance on the steel. A welder, crouched by the cope stiffener, spotted a hairline crack at the weld toe during a bolt retorque. It was thin as a pencil mark, but ran longer than his thumb. He mentioned it to a rigger, who shook his head and suggested magnetic particle testing or dye penetrant, methods that could reveal hidden flaws without tearing anything apart. The rigger's voice was flat. "This ain't right." The site superintendent listened, but waved off the concern. He logged the 25mm deflection as routine settlement, classifying it as low risk. The crane had to keep running. Every hour offline cost the project $2,000 in lost revenue, not counting the threat of daily penalties. Non-destructive testing was skipped to avoid delays, and inspection cycles stretched thin. Maintenance bonuses were tied to uptime, rewarding those who kept the machine moving, not those who slowed it down for caution. In the break room, workers traded stories about the old days, how before OSHA, men relied on their senses and gut instinct. On this site, warnings traveled by word of mouth, rarely making it into official logs. The engineer assumed the temporary core ties were in place by the third climb. The contractor never corrected him. Communication broke down, and with it, the last chance to catch the silent fatigue growing in the steel. The culture of speed and silence left the base exposed, its flaws hidden beneath layers of urgency and routine. Metal fatigue in the H-frame base began as a microscopic flaw, invisible to the naked eye, but relentless under the crane's daily rhythm. Each startup, every idle vibration, and the repeated swing of the boom sent waves of stress through the welded joints. At the weld toe, where the geometry forced the steel to bend and flex, a crack just 0.5 millimeter wide began to grow. Paris law, dA/dN equals 2 times 10 to the minus 12, delta K to the third, mapped the pace. With each cycle, the crack lengthened, the stress intensity factor climbing from 11 to over 40 megapascals times the square root of meters. The process was slow at first, measured in microns, but exponential. Doubled stress meant half as many safe cycles. Beach marks, each just a fraction of a millimeter apart, recorded the history of these advances, like rings in a tree. By the time the crack reached 12 inches, a critical length for this design, over 1 million cycles had passed. Miner's rule, the engineer's tally sheet for lifetime damage, showed the cumulative effect. Every idle hour, every gust of wind, every load added to the total until the sum reached 1. The steel's resistance, already weakened by corrosion in the Pacific Northwest's damp air, finally gave way. 8 M24 bolts sheared in quick succession. The base slid north, friction lost. The mast buckled. There was no sudden overload, no extraordinary force, just the silent, mathematical certainty of fatigue. The collapse unfolded exactly as the equations predicted, each stage matching the forensic models built after the fact. The inevitability was written in the numbers long before the final fracture ever reached daylight. Washington Labor and Industries investigators spent 6 months in the laboratory, piecing together the story hidden in fractured steel. Under the scanning electron microscope, the base welds revealed striations, parallel lines just 1 to 5 microns apart, each marking a tiny advance of the fatigue crack over thousands of cycles. These beach marks, distinct and regular, matched the operational history logged on site. Hardness tests measured Rockwell B values between 80 and 90, confirming the steel had not lost its basic strength, but Charpy V-notch impacts told a different story. A 20% loss of toughness near the welds, likely from corrosion in the humid northwest air. No brittle cleavage, no signs of overload, just the classic fingerprint of metal fatigue. The evidence was clear. The collapse began at a microscopic flaw, growing steadily until the final fracture, sealing the chain of cause beyond any doubt. Legal consequences followed swiftly. In 2011, a King County jury awarded Warren Yeakey $1.45 million for injuries and trauma, citing negligence in the base's design and inspection lapses. The Ammon family's wrongful death lawsuit, filed against the contractor and engineering firm, settled in 2015, part of more than $5 million in total damages, including property loss and a halted project. But the most lasting impact came from the State House. Washington lawmakers passed Senate Bill 6027 in 2007, creating some of the strictest crane regulations in the country. The law required annual third-party certifications for every crane, mandatory operator training, and independent base design reviews using finite element analysis. Non-destructive testing became routine, and clear documentation replaced word-of-mouth approvals. Within 5 years, state data showed crane-related fatalities fell by half. For families, workers, and city leaders, the reforms stood as a response written in statute, a direct answer to the failures that cost a life and scarred a city. At 4:15 p.m. on November 16, 2006, a 210-foot tower crane fell in downtown Bellevue, killing 1 resident and causing over $5 million in damage. Investigators confirmed that metal fatigue in the base's H-frame, compounded by missed warnings and a lack of required non-destructive testing, led directly to the disaster. Despite detailed forensic analysis and new laws like Washington's Senate Bill 6027, which cut crane fatalities by 50% within 5 years, some questions remain. The original engineering correspondence and full decision trail for the H-frame base have never been publicly released. What is clear: economic pressures, unconventional design, and skipped inspections combined to expose fatal weaknesses. Today, every major crane in Washington is subject to independent certification and stricter audits. The Bellevue collapse stands as documented evidence that rigorous standards and open communication save lives, lessons written not in theory, but in steel and loss.